Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our present topic is that hook removal during drafting. So, the hook removal during drafting, here we will discuss in two stages. In first stage we are discussing the simplified model, okay, just to understand the hook removal, and in next stage we will go in depth, but there we will try to discuss the various conditions, various situations we will discuss, and we will not go in depth of the derivations, but we will show the derivation and we will see their implication. Okay. First, let us discuss the hook removal with the simplified model. So, hook removal is the basic necessity in the drawframe, basic function. One of the important function in drawframe is the removal of hooks in card sliver. So, this is the direction of sliver coming out from the carding machine, and based on that we term as leading hook, where the hook is at the leading end. So, this is trailing hook. So, at the trailing end the hook formation is there. If the direction is in this direction and both side hook, where the hooks are present in both the sides, straight fibers will be there without any hook and others. So, this is the hook, it is neither hook, it does not fall into all the above categories. So, this is clumped fiber, so entangled fiber. So, that will be treated as others. So, here in this section we will consider the trailing and leading hook majorly. Now, if we see the proportion of hook present in the card, so it changes with the speed. So, it is this data is from an experimental data, but average the hook percent is follows this type of values. So, in if the Drawframe speed, so the hook percent changes with the Drawframe speed. So, in Drawframe speed, if it is slow, the proportion of hook is 19% leading hook, trailing hook is maximum here, then both end hook is 8%, without hook 23% and others entangled fibers are 3%. So, the trailing hook is maximum in case of slow Drawframe speed, but for high production card where the Drawframe speed is increased very high. So, in that case the leading hook increases to approximately 31% and trailing hook reduces. and we will see here the both end hooks are almost same, and the no hooks without hook. So, that reduces, that means straight fiber reduces, which is actually due to the increase in mainly leading hooks, and others are increasing also from 3 to 16%. That means, when we increase the doffer speed, this type of other type of hooks also increases significantly. So, you can see here at different speeds how the leading hook trailing hook proportion changes, okay, no hooks. Now, let us try to understand the mechanism of hook formation, and hook is basically formed mainly in carding, and drawframe is responsible for removal of this hook. So, before we understand the hook removal principle, first let us see the how the hook is generated at the carding machine. So, this is the cylinder which rotates say clockwise, and doffer is there, the wear points are oriented in opposite direction, although at their point of the closer point of transfer, the movement in the same direction, but the cylinder moves at much higher speed than doffer. So, how the trailing hook is generating? Now, see, as the cylinder doffer transfer point, at that point, this is the cylinder doffer transfer point, the leading end of the fiber gets lashed onto the doffer wear point. So, this is the leading end. So, leading end is lashed into the doffer wear point, and this is the leading end, and trailing end moves faster. This is the trailing end moves faster with the cylinder surface. So, leading whatever, suppose let me draw the fiber before it is coming. So, this is the fiber which was coming. This leading end is lashed into the doffer surface. So, sorry, let me draw once again. So, this leading end, this is the leading end which is first end fiber gets lashed into the doffer wear point, okay, and the trailing end, this trailing end. So, when it is lashed into the wear point, its speed reduces, because it will start moving at the doffer speed, but the trailing end is still under the grip of the cylinder, which moves at very fast speed. This is the position of trailing end. Trailing end moves faster and get released from the cylinder surface, okay, cylinder surface, and forming a trailing hooks. So, this is released here. So, the thing which is happening here, this is the trailing end, leading end is first lashed into the doffer surface, and this end which was trailing end, this is actually coming at high speed and it forms in this fashion. This is released by the cylinder wear point and comes into the surface of the doffer, and ultimately the formation will be, this is the form and in this formation. So, then when it is going out and it will come out as a trailing hook. And leading hook formation, you can see if the fiber is held firmly by both cylinder and doffer. Earlier what happened? Fiber was held firmly by the doffer, but cylinder releases the fiber as it is and forming the trailing hook. But here what happened? Doffer is gripping the fiber, because doffer will take the fiber leading end and the other end is held by the cylinder. There both of them are holding the fiber firmly, and the trailing end of the fiber gets whipped up when the transfer happen from the cylinder to doffer. So, that means this end, what happened here, it will be forming this type of. So, trailing end will and doffer will take out this material, this portion, and it will be straightened, and this end will be whipped up, okay, when the transfer is taking place, because the when transfer is taking place, the holding power of doffer is higher than the cylinder. So, doffer will definitely take away the fiber, but it will be just like it will be whipping out at this end. It will be whipped out at the and form the trailing end, trailing hook. So, this is the trailing end, it will become the trailing end. The second possibility is that the fibers having a leading end hook on the cylinder. So, fibers having leading end, so it will directly be simply get peeled off by the doffer. So, this is trailing end, leading end, and it will be simply transferred to the doffer surface and maintain the leading hook. Okay? It will simply get transferred. Earlier what we are discussing, it was the straight fiber coming to the doffer surface, but when the fiber is already having a leading hook, it will get simply transferred. Okay? And the third possibility is that when the straight leading end, okay, straight leading end of the fiber appears, approaches the doffer transfer point, due to the sudden drop in air speed, it gets buckled. So, here what happened, due to the high speed of cylinder, the air stream speed will be high, but when it comes to the doffer, the due to slower speed, the sudden speed changes. Now, the thing is that a fiber, suppose it is moving at very high speed, and when suddenly it is transferred to the doffer where air speed is less here. So, during that sudden change in air speed, the fiber gets buckled. The opposite thing happens, we will discuss in the rotor spinning. In rotor spinning what happened? due to the conical shape, the buckled fiber gets straightened because the air stream speed increases, which takes the leading part the at higher speed and trailing part at lower speed. So, it gets straightened, but here the opposite thing happens. Suppose this is the and the leading part. So, leading part will have slower speed when it is coming close to the doffer, and trailing part is coming at high speed. So, it will form the buckling. So, that buckle, it gets buckled and gets transferred to the doffer with a leading hook. So, this is the third possibility. Now, we can see as the doffer speed increases, the major hook, that is trailing hook, reduces, and the major hook means trailing hook and minor hook is a leading hook. So, minor hook increases with the increase in cylinder speed, major hook increases, minor hook reduces. With the lighter sliver, so trailing hook reduces and both trailing hook and leading hook reduces. That means, if we have the thinner sliver, so with a low linear density, the hook can be reduced, both the hooks can be reduced. Fiber length, both type increase, as the increase we increase the fiber length and the both the hooks increases, because there is a chances of getting folded, and increase in leading hook is more, and fiber denier, as the fiber becomes coarser, the trailing hook increases, but leading hook reduces. So, these are the different parameters or factors on which the hook depends. And fiber friction, if the fiber friction increases, both the hooks reduces, because there will be better control over the fiber hook formation. Okay. So, that is it, there will be chances of fiber getting straightening. So, let us consider a fiber with hooks. Okay, this is the hook. Now, we will discuss the hook removal one by one, trailing separately and leading separately. The fast drawframe passages bring down the number of hooks and increases the mean fiber extent. So, if we use the multiple drawframe passage, so in fast drawframe passage, the hook percent will reduce, okay, and the fiber extent will increase. Hook removal efficiency is less in the second drawframe passage. So, the hook removal efficiency is maximum in the first drawframe passage. Trailing hooks are on average removed more easily than leading hook. So, that is actually true, because let us discuss here. We have a drafting zone here. Now, this is the front roller, this is the back drafting roller. Now, here the fibers are there and here the fibers will be. So, if the draft is say 10 or maybe say 10 draft. So, number of fibers here if it is 100. So, at under the control of grip of the front roller, the number of fibers will be 10 times less, 10 fibers. Okay. So, what happened? Suppose there is a trailing hook, let me draw in a different color. So, a fiber with a trailing hook is there, and this trailing hook portion will be in contact with the fibers which are moving at slower speed. So, due to the frictional contact, this slow moving fibers which are in larger proportion will try to straighten this hook due to the frictional contact. Okay. That is why the chances of removal of trailing hook, okay, trailing hooks are easily removed. But on the other hand, if we consider a leading hook, so there is a leading hook here, okay, but this will only be removed by the pull of the faster moving fiber, but faster moving fibers, number of faster moving fiber are less, relatively less than the hooks. So, here the force generated by the fibers which are lower in number will be relatively less. So, removal, chances of removal will be little bit low, and that is why it cannot be easily removed. Leading hook is difficult to remove, but it removes because of the fiber contact. So, trailing hook is easily removed. Now, let us consider one hook where B is the bending force. So, this is the bending force which resists the hook removal. So, hook is there. Now, we have to, if we try to remove it, we have to remove against this bending force. So, that is the bending force which resists the hook removal. Hook has already been formed. The draft is D, mu is the coefficient of interfiber friction, because the interfiber friction is very important, because due to that interfiber friction the fiber, slower or faster moving fibers try to pull and hook is being removed. G is the average interfiber lateral pressure. So, there must be some lateral pressure interfiber, otherwise the frictional force is will not generate. So, G is the average interfiber lateral pressure, and this lateral pressure come from the top roller pressure and the fiber rigidity. So, that it comes. So, average peripheral length of fiber cross section. So, peripheral length means average peripheral length, that is periphery of the fiber. K is the average ratio of peripheral length of fiber in contact with other fiber to the total peripheral length of the fiber. Suppose the total peripheral length of fiber is something. So, but in total peripheral length, but fiber which is effectively under the contact of other fibers. So, K is less than 1. So, higher the K, if K is 1, that means total fibers are throughout the fibers length, it is contact with other fibers. That is not possible, but K is the ratio. So, higher the K means the better will be the hook removal efficiency. L is the length of hook as it is shown, hook portion of the fiber, and x is the surface area of the hook portion of the fiber in contact with the fiber moving at the back roller speed. So, x is the surface area of hooked portion which is actually contact with the fibers moving at the slower speed, expressed at the fraction of as the fraction of total surface area of the hooked portion in that region which is in contact with other fibers. So, total fibers are there, and which is that this hook portion is contact with the different fibers, okay, which is moving at the speed of the back roller and moving at the speed of the front roller. So, suppose it is a 10 fibers are moving contact with the back roller, okay. And so, 10 is the surface area, and here it is say 5 is the surface area contact. So, surface area in contact in the proportion of the with the moving at the back roller speed. So, 10 total area is surface area is 15. So, 10 by 15 is that x. So, surface area in contact, surface area in the hooked portion. So, in the hooked portion only where fiber is in contact with the other fibers moving at the back roller speed, okay, expressed as the fraction. So, this is the fraction here. Now, the resisting force of the hooks. So, hook has got two type of force, one is resisting force, another is which will try to remove the hook. Now, what are the resisting force you see? So, bending resistance of fiber which resists the removal of hook B, and frictional resistance of slow moving fiber with the peripheral contact. So, slow moving fibers, so that will, so when we are talking about the removal of leading hook, so let us see draw. So, this is the front roller and back roller. So, leading hook is there, we want to remove the leading hook, and here this is the fast moving fiber shown in the red color. Now, here the one is the bending resistance which definitely resists the hook removal of leading hook. Now, frictional resistance of the slow moving fiber. Now, there will be fibers which will move at slower speed. So, I will draw another. So, this is under the control of the back roller. So, the blue color is slow moving fiber and red color is fast moving fiber. Now, here if the frictional resistance of slow moving fibers is high, then it will resist the movement, the hook removal, and if the frictional resistance of the fast moving fiber is high, then it will assist the hook removal. So, and that depends on the peripheral contact, peripheral contact. So, and that more the higher the contact, higher will be the that resistance. An assisting factor is that peripheral contact of fibers which moves at the front roller speed. So, here with the red fiber, that is helping the hook removal, but with the blue fiber it is resisting the hook removal. So, total peripheral length in contact with other fibers is Kp. Okay. P is the peripheral length and K is the fraction of the peripheral length and with the contact with the other fibers. So, P is the average peripheral length of fiber cross section and K is the average ratio, as we have discussed, of the peripheral length of a fiber in contact with other fiber to the total peripheral length. So, K is that is if it is x. So, x by p. So, x equal to Kp. So, that is the value. So, x is the total peripheral length of fiber, total peripheral in contact with other fibers. Kp and average area in contact hooks with the fibers moving at the back rollers. So, at the speed of the back roller Kp, so L is the length of hook portion of the fiber and x is the surface area hook portion of the fiber in contact with the fibers moving at back surface speed as a fraction of the total surface area of the hook. So, if we then we multiply by L and x. So, Kp Lx is the average contact area of hooks with the fibers moving at the back roller speed. So, this is the total peripheral length average contact. That means, this will actually resist the removal of hook or leading hook. So, that average force opposing the movement of the hooks portion at a speed faster than resisting. So, that this is the area and where mu is the frictional coefficient and G is the normal force. Okay. Mu is the coefficient of friction and G is the interfiber normal force, that is lateral force. So, this is the total force which actually opposing the hook portion to move faster speed, that means it is resisting force. So, resisting force of hook removal is mu G K P L x, that is the resisting force. So, that is moving at the back roller speed. So, which is actually resisting that, as we have discussed. Now, the fraction of fibers surface hooked at the hook portion in contact with the fibers moving at the front roller speed. X was the fraction moving at the back roller speed, that means 1 minus x is the fraction moving at the front roller speed. So, let us try to see the assisting force. So, average force assisting the movement of the hook portion at a speed faster than the rest of the fiber. So, what will be the assisting force? In place of x we are using 1 minus x, that is the assisting force. Now, hook removal will only happen if the assisting force is more than the resisting force. So, resultant force assisting the removal will be this minus assisting minus resisting minus B. What is B? B is the bending force also there. So, so this assisting force should overcome the resisting force and the bending force, then only the leading hook will be removed. So, this is the equation, this is the assisting force in contact with the other fibers in the drafting zone, resisting force in contact with the leading that hook portion in contact with the other fibers in the drafting zone, and B is the inherent hook removal, the bending force of hook removal. So, that if these two can be overcome, then only leading hooks can be removed. So, it comes out to be this minus mu g k p l multiplied by 2x minus 1 plus b. This is the relationship. Now, assuming 100% fiber surface area in contact with either fast moving surface, fast moving fibers from the front roller surface speed or at the back roller surface speed. So, that if we assume there is a 100% contact, then so x by 1 minus x will be d. That means, its a total draft will be x minus 1 by x, that is the number of fibers with the front roller speed and number of fiber with the back roller speed. So, this is the number of fibers in the with the contact with the back roller speed, which is in contact, and this is at the with the front roller speed. So, 1 minus x. So, x by 1 minus x will be d if we assume the 100% surface contact. So, number of fibers, it is proportional to the number of fibers moving at faster speed and number of fibers moving at slower speed. So, if we replace there, so d, this can be rearranged, d minus x equal to 2x minus 1 by 1 minus x. So, d plus 1 is 1 by 1 minus x, that we can do it. So, from these two relationship we can get 2x minus 1 will be d minus 1 by d plus 1, because 2x minus 1 we have to replace in earlier relationship. So, resulting assisting force is, we have actually for leading hook we have derived this, where 2x minus 1 we have got in terms of draft. So, minus mu g k p l and multiplied by 2x minus 1 plus b, that 2x minus 1 is replaced with this formula. So, resulting force assisting the removal of leading hook is minus mu g p l multiplied by d minus 1 by d plus 1 plus b. So, these are the this is the resultant force, and from there to remove the hooked portion, leading hook portion, that the hook portion should be moving slower than the average movement of the fiber around the fiber. So, if we want to remove the trailing edge, so this is the leading leading hook relationship. Okay. Now, we will consider the removal of the trailing hook. Now, trailing hook we can see this is the condition. Here there are fibers. Now, we will see draw one fiber with the trailing hook, and these are the fibers under control of the back roller, and the green color, this is the control of the front roller. Now, here to remove the trailing hook, the hook portion should be this hook portion, it should be moving slower speed than the average movement of the fibers. Okay. So, average fiber movement around the fiber surface. So, this hook portion should move slow at the slower speed, because that will be actually pulled. Okay. And we have already discussed the resultant force assisting the removal of leading hook is this, that we have discussed. Now, let us see for trailing hook, the resulting force assisting the removal of the trailing hook will be, in place of 1 minus x, it will be x, because the proportion here is x and this is same equation will be there, but the only the proportion will change and we get this relationship mu GPL multiplied by 2x minus 1 minus b, and 2x minus 1 we have got d minus 1 by d plus 1 as d increases. So, when the draft increases, so d minus 1 by d plus 1 will increase. Hence, the chances of removal of trailing hook improve. But on the other hand, we have seen for trailing hook, for leading hook, this is not the case. Okay. So, for trailing hook we can increase the draft and we will get the improvement. So, as this will increase with the draft, so this value will increase. So, we will get the resultant force assisting the removal of the trailing hooks. So, this is all about the basic understanding of hook removal in Drawframe, and in the next session we will discuss, as I have mentioned, the hook removal theory, which is latest theory, but will not go into depth of the individual derivation, but we will discuss various stages of hook removal, the theory. This will be, that will be only basically theoretical approach for just for basic understanding. Till then, thank you.